Hello guys, this is Moksha Shah from TE Electronics. So today I'll be showing you all an experiment on practical integrator using op-amp OP07. First we'll be implementing the integrator and then study its frequency response. If we talk about the ideal integrator, the problem with it is that the gain current is nothing but the capacitive reactance upon the input resistance. If we talk about the capacitive reactance, which is nothing but 1 upon 2 pi fc into Rn, and then if at a lower frequency f is equal to 0, then gain will become infinite, so the capacitor will be open circuited. So because of which the input offset voltage will make the op-amp throw the op-amp into saturation, because the op-amp will be in open loop op-amp. So we use a practical integrator. In this practical integrator, we connect a resistance in parallel with the capacitance, so that the capacitor does not go into open circuit, and until the capacitor is dominant, the capacitor becomes dominant at a high frequency. So at that frequency the R2 will reduce and the gain will also reduce. So let's see the calculations. Given that lower cutoff frequency FA is 1 kHz and the upper cutoff frequency FB is 10 kHz. In this, I am assuming the feedback capacitance to be 10 nanofarads. If we talk about the FA is nothing but 1 upon 2 pi RF and FB is nothing but 1 upon 2 pi R1 CF. So I will get the values of R1 and CF accordingly. So let's just start building the practical integrator. For that, I'll be opening the LTspice. Okay, so over here, if I've already built the circuit, for that just right click on the voltage. So you will get this box. Click on sign, give the offset as 0, amplitude as 1.2 volts and frequency as 1 kHz. I'm showing you all at 1 kHz, that's why. Click on OK. Now go to run. Click on the input side. Now click on the output side. So you all are getting it as a negative cosine wave. So if you want to see the V out, so you can just left click on V out and drag this to the peak. Yes. So over here I'm getting the value as 8.43, the same value I have noted in my observation table. I'll show you all. So over here at 1 kHz, so this is 16.85, that is nothing but the double of the V out value for writing voltage peak to peak. In the same way I have written the V in also. We have taken 1.2 into 2, that is 2.4. Now to get the gain in AV, which is nothing but V out by V in, and gain in dB is nothing but 20 log of gain in AV, or you can write it as 20 log of V out by V in. So I've taken different frequencies to check the output of the practical integrator and how does it work. I've taken highlighted the values of the upper cutoff frequency and the lower cutoff frequency. As we go further, you all have a clear understanding about the integrator much more. So I have shown you all for the sine wave as an input. So I'll be showing you all for the square wave as an input also. So for that, first I'll open the new one. For opening that new one, so let me open the LTspice. I'll open the file, go to the open. Since I have built a new, I'll take this input square wave. I'll just cut it off. Yeah. So I'll be giving the square input. For that, just right click on the voltage, give V initial as -1, V on as 1, T delay as 0. Don't forget to click on pulse. T rise as I'll be taking it as 0.01 micro, and then T fall will also be remain same, 0.1 micro, and T on will be nothing but 0.05 milli, that is the half of the T period, that is 0.1 milli. So 0.1 milli is nothing but 10k hertz frequency. Click on OK. So I'll just click on run. Click on the input side, click on the output side. So as you all can see, at the input side you all are getting a square wave, and at the output side you all are getting a triangular wave. This starts from the upper side just because the capacitor is taking some time to charge up, and when it gets charged up you get a proper triangular wave. I'll show you all for the lower frequencies also. Just right click on the pulse, and now I'll change it to 1k hertz, that is 1 milli, and T on will become half of it, that is 0.5 milli. Click OK and then run again. So I'll change the transition time for a proper output. I'll make it 10 milli. Click on enter. I'll run it again. So yes, you all can see you all are getting an exponential curve. So this is because it is not changing to complete ramp. The capacitor charging and discharging is inherently exponential charging and exponential discharging, because of which you are getting an exponential curve. As you go on increasing the frequency, you will get a proper triangular output as we saw previously. So now for the triangular input, again right click on the voltage. The first three readings will remain same. Change this to 0.05 milli and T fall also to 0.05 milli. The T on will become 0 and the time period will become double of 0.05 milli, that is T rise or T fall, that is nothing but 0.1 milli. Click OK. Now run it again. Click on the input side, click on the output side. Yes, I'll change the transition time again. I'm just clicking right on the transition time. Click enter, run again. So yes, for the input triangular wave, you all are getting a sinusoidal wave for the input triangular wave. The same thing I've shown in my Word file. I'll show you all again. So this was the sine, this was the square input, and this was for the triangular input. Now I'll show you all for the frequency response. I'll just open the LTspice. Again, I'll open one of my file which I've made it already. Open. I'll just go to the frequency response. You all can just make the changes in the same circuit. Just right click over here. You all might have a pulse or a sine selector. Click on none and make the AC amplitude as 1 and click on OK. Now go to the simulate, go to the edit simulation command, go to the AC analysis, click on decade, give the number of points per decade as 500, start and stop frequency as 1 and 100k. Click on OK, click on run. At the output side, you all are getting a frequency response and the dotted ones are the phase response. To get only the frequency response, on the right side, right click and you will click on don't plot phase. So you will get the frequency response. If you right click, you all can just simply change the color whatever you want. If you left click on V out, you get a drag option. I'll just drag it to 1k hertz. So like I'm trying to get it as exact 1k hertz. Now again left click and drag it to 10k hertz. Yes, I got the 10k hertz. Now you all can see at 1k hertz I'm getting the dB as 16.94. That is from 20 to 16.94, that is drop of 3 dB. If we talk about the gain is being constant till 1k hertz, and after that it gets starting attenuating, that is it decreasing at minus 20 dB per decade. Minus 20 dB per decade. And if we see at the upper cutoff frequency, exactly at 0 dB you are getting an upper cutoff frequency, and the gain is then further going on decreasing. So this was about the frequency response. Now I'll be showing you the phase response. Just right click again, click on OK. Now at the left hand side, right click and click on decibel and say Don't plot the magnitude, so you will get the phase response. So this was the phase response of the practical integrator. So I'll just open my Word. So the same thing I've shown over here. This was the frequency response and this was the phase response. So in this experiment we saw the frequency response and the different inputs, that is sinusoidal wave which was giving me an inverse cosine wave, a square wave was giving me a triangular wave, and a triangular wave was giving me a sinusoidal wave. Thank you.